Welcome back. If you are just starting this series, it is recommended to refer to part 1, but you can still watch this video as a reference. In the last video, we rendered our button backgrounds using a texture atlas which gives us full control over the visual look without unnecessary complexity. In this video, we will go through the new code and updates needed to display the button's text labels. To get started, let's update our use namespace statements. This will make certain functions and structs available to us in shorthand notation. To add to our structs such as button and button config, we create new structs consistent with the previous ones. We will assign buffers to each label to optimize for many UI components rather than one single buffer for the entire UI. In game engines, buffers are typically assigned per entity in a similar fashion and updated independently. We also create a label config with important positioning and sizing parameters, as well as wgpu objects that will be discussed later. Soon we will need to store glyph text character information in a vector, as well as some UV information related to the glyph's texture. Now we actually create the reusable function for calculating a glyph's UVS. Of course, it is dependent on the atlas dimensions. That is because UVS are simply proportional numbers between 0 and 1. Let's also adjust the vertex struct, as it will not only accept a z-coordinate, but also RGBA color information. Of course, since we will be supplying additional data on the vertex, we will need to update its buffer layout. As you can see, the offset signals the start to the attribute in a flat vertex while the format signals the length of that attribute. Here we begin our new functions with createLabel. Like our createButton function, it accepts some shared wgpu objects as well as the basic configuration information. We start with the default color definition, which will not be used as it seems as this time. The Fontdue text layout is created with a consistent orientation as our code expects along with the desired text and font size. Let's continue by instantiating our vertices and indices for the text label. Be careful to specify the type of the indices, or else your buffer won't match the format of your data. You can also see the start to our glyph loop. This is necessary to draw character textures from our atlas to any word combination. The primary concern at the beginning of the loop is collecting the character's relevant dimensions. In this portion, we will first determine the origin point of this glyph. We do this straightforwardly with position data. Then we use the dimensions to build our quad corners logically. Make sure to follow the correct order. Otherwise your quads are unlikely to display properly. If you need to do any testing, feel free to add the commented hard-coded parts to verify functioning. Now we get to calculate the NDC positions, which are added to the vertex data. As mentioned in part 1, NDC positions are simply proportional to the window size and range from -1 to 1. For this reason, we take advantage of the equations shown. Next we will calculate the glyph's UVS, as these are added to the vertex as well. Simply leverage the function we implemented earlier on the glyph info struct. Remember to follow the correct order here as well. To wrap up this loop within our createLabel function, we will simply add our data to vertices vertex data. Also pay special attention to how the indices are assembled. They are determined very similarly to the quads for the button backgrounds, but work for many quads in a row. Now we get to write our label buffers. We only need to write the vertex and index buffers here, using the data we just prepared. This is relatively self-explanatory. ByteMuck helps assure the data is in a contiguous format acceptable to the GPU. We also need to create a bind group per label. Much like with the buttons, you'll notice that the bind group features a binding number 2, which feeds a uniform buffer to the GPU. A uniform buffer is just rarely changed data, in this case, a render mode. The other bindings, like with the buttons, specify the texture atlas and sampler used. Pretty standard for a texture-based binding. Finally, we wrap up this function by returning the data needed during the draw calls. Now we can move on to another important function in our button label setup. This function will take a set of configuration options and create texture atlas, wgpu texture, and dataset of glyph information. We begin by specifying some early usable values as well as some empty values. The hash map will help us store the data we need in a dynamic, key-based fashion. Now, here we have another characters loop. However, this is looping through a different set of characters, the whole alphabet. Thanks to Fontdue's incredible efficiency, we can rasterize within a loop during our app startup. We can also leverage that efficiency later for text inputs. You will see some wrapping logic here in case the characters spill over the edge of the texture. At the end, we actually manually set this rasterized bitmap data into a new array, in a new position. ChatGPT is your friend. Finally, we wrap up our relatively simply loop by taking care of the glyph info data. We also prepare the variables for the next pass-through of the loop. Now, in typical wgpu fashion, we will create our texture before writing it. Remember, layers are not needed as we are not using 3D textures. Bitmaps are also not needed as our objects will not be seen at a distance. Besides that, it is two-dimensional, with only the red channel being used for the text. The text will not be red though. Finally, we write the texture. As mentioned in part 1, we specify our origin, as well as use the necessary arithmetic or lack thereof to determine bytes and rows. Now, here is an update to the original buttons code. Make sure to include a color as now. We will be passing color through on the Vertex data. Here you can see passing that data through. Now we are ready to bring in our chosen font. I chose Inter, which is completely open source and beautiful. In your initialize core function from part 1, after you obtain the device and queue, we will start loading the font. Specify a path and literally include that byte data easily. Then use Fontdue again to read in those bytes. Take advantage of our function for creating a texture atlas. And supply any character that you want to display in your labels, including spaces. Now we have some typical wgpu texture-related objects. Your sampler will share the same settings as the buttons. Now, because we are actually going to use the same bind group layout between all labels and buttons, we update that here. Make sure to add binding number 2 for the uniform buffer data, which we will create next. Here you can see 2 uniform buffers being created, which will be assigned to the number 2 binding in the bind group layout. Button backgrounds get a render mode of 0, while button text gets a render mode 1. This simple way of passing in data to the shader will allow us to display very different data to the screen. Let's go ahead and use our createLabel function and pass in everything we've prepared thus far. You'll notice that the Z position is 0.01. This is critical to displaying in front of the button background. Remember, 0 is origin, so Z increases outward from the screen, so lower Z values appear on top. Create a second label too, then wrap them up in a simple vector. Now, to assure that the button labels display over top the button backgrounds, we will need to enable depth stencil testing. This is the primary way in which GPUs determine what is visible to the camera and what is occluded in 3D space. First, we create a depth texture, much like our other textures. Then we also specify a state for our pipeline. Depth to 4+ offers high compatibility along with performance. The less comparison parameter simply specifies that fragments at the same location will be drawn if the depth value is lesser than the current. Here you will see just the portion of the render pipeline, as it is so big. Besides adding the depth stencil state, the other updates are relatively harmless. Next we can move to updating our render pass in our render loop with depth stencil settings as well. You can try altering the store property to see if you can get increased performance. Now comes the last update to our main res file. Here we iterate over the labels and draw all their vertices and indices just as with the buttons. Now here is our updated fragment shader. This should bring together the render mode and how we can leverage one shader and pipeline for our UI. Notice how the red channel is used to specify the opacity on the text. Our Vertex shader is updated just a bit to manage color and 3D positioning. Here is a shot of the final outcome when ran with Cargo. As you can see, the text is not perfect. It has some visual artifacts and mispositioning, but it is great for a prototype. Onward, if this video helped you, please comment or subscribe. That will lead to more obscure topics being covered and more investment in the channel. Also note that you can find all the code for this project at my GitHub profile, at Alex the Goodman.